Good morning, I'm Axel Nardin, and in this talk I'm going to present one of the latest works of my lab regarding few-shot learning for document layout analysis. Document layout analysis is the task of identifying different components inside of a document page, and this can be done in two main ways. The first one relies on bounding boxes, while the second one relies on pixel-precise semantic segmentation. When working with ancient documents, the preferred approach is usually the latter, as the components of a page are typically very intertwined and make it difficult to rely on a bounding boxes approach. Here you can see the desired output of our network. Compared to general-purpose semantic segmentation, document layout analysis poses some domain-specific challenges. The first one is the high degree of degradation in the pages and the inconsistency in the capture conditions for the instances of a dataset. Then we have the difficulty in obtaining large amount of precisely annotated data because it's a very time-consuming task and also requires some domain knowledge. This is why we work in a few-shot setting. And finally, we have the very high structural similarity between the different components of a page, since we usually try to distinguish between different types of text, and therefore the differences between them are very subtle. That said, the main contribution we bring with this paper is the ability to achieve close to state-of-the-art performance while relying only on a fraction of the data used by the competition models. And we do so by using the following framework, which is based on three main components. The first one is a backbone segmentation network, in this case a deep-tree. Then we have a dynamic instance generation model, and finally a segmentation refinement model. In the dynamic instance generation model, we extract two sets of patches from the original image. The first one is a set of non-overlapping patches which are kept consistent between the training and inference phase, and we call them baseline patches. While the second set is represented by random crops dynamically generated at each epoch only during the training phase. These two sets of patches are then combined and fed into the segmentation backbone, which will then provide us with the final semantic segmentation maps, which we will compare to the ground truth in order to train our model. For the segmentation refinement model, we combine the output of our segmentation backbone with the output of the popular Savola thresholding algorithm for document binarization, and this way we are able to achieve much more accurate maps when compared to the ground truth ones. Here you can see some of the results obtained through the ablation study we conducted in order to prove the effectiveness of the module we introduced in our framework. And in particular, you can see that when we combine both the segmentation refinement model and the dynamic instance generation model, we achieve around 10% improved performance for all the metrics compared to the baseline framework. As for the quantitative results, we compared our model with some popular semantic segmentation networks, as well with the current state-of-the-art in document layout segmentation. And as you can see, our model achieves around 1% lower performance compared to the current state-of-the-art, while outperforming all other methods. One important thing to keep in mind, though, is that all the other models were trained on the whole dataset, while our model was trained only on 2 instances for each document class. Finally, we present some qualitative results in order to show the actual quality of the segmentation maps provided by our model. This concludes my presentation. Thanks everyone for your attention.